Hello everyone, this is Sonam Acharya. I am a PhD student working in the Power Management Lab of Indian Institute of Technology, Kanpur, India. So in this webinar, I am going to discuss about microinverters, the challenges and opportunities. So, with this solar photovoltaic energy currently being one of the most important non-conventional sources, that is renewable sources, recently renewable integration has seen a significant surge in installation of rooftop photovoltaic systems. So, for residential rooftop installations, we generally have two kinds of system that interfaces the PV panels and the household loads. So, let's see the first one. Here, the PV panels are connected in series and then the output is given to a DC to AC inverter. So these inverters are generally known as string inverters. Here are the specifications for a typical string inverter. As we can see, the input voltage of this inverter is generally more than 600 volt, and they have power rating in the range of few kilowatts, and these inverters are operated generally at low switching frequency. Now let's see some of the commercial companies which manufacture these string inverters. So first we have this company called SMA, which produces string inverter with a power rating of 50 kilowatt. Then we have ABB, which produces inverters up to 8 kilowatt power rating. Then again we have Sun Group company, which produces till 6 kilowatt. Now let's discuss the second system. Here, each of the PV panels is connected to a DC to AC inverter, and then the outputs are connected in parallel, supplying the household load. So each of these inverters are known as microinverters. Now here are the specifications for a typical microinverter. Here, the input voltage is in the range of 48 to 60 volt, which is low, and these inverters have power rating in the range of 500 watt to 1 kilowatt, and the inverters are generally operated at high switching frequency. Now let's see some of the commercial companies which have been manufacturing microinverters. First we have this N-phase. As we can see in the graph, over the years, the power rating of the manufactured microinverters has been increasing. Now we have this ABB, then Saipo Energy, and also we have Apparent, which have been manufacturing microinverters. So we saw that these microinverters have low input voltage, whereas they have to supply the loads which operate at higher AC voltages, that is 110 volt AC or 230 volt AC. So as the power rating of this microinverter goes up, what this low input voltage does, it leads to high input current. So at higher power rating, due to this high input current, the efficiency of microinverters becomes very poor. So what is generally done to have an efficient power conversion is two or more microinverters are connected in parallel, but this solution is not cost effective. Now the question is, do we have uh, any other cost effective solution for this problem? So in this webinar, we'll try to find out the answer to this question. Well, let's have a look on the outline of the webinar. So first, I'll discuss the power electronics behind the microinverters. Then I am going to walk you all through some of the existing technologies for this microinverter. Then we'll be comparing the existing technologies. Then we'll discuss some of the challenges faced by the existing technologies. Then I'll discuss the proposed solution, and then followed by conclusion. So now let's understand why this microinverter system is better than the string inverter system, that is the series connection of PV panels. In fact, the series connection of PV panel is limited by two factors. The first one is we have limited availability of space, and the second one is the series connection of PV panel actually poses a serious problem under partial shading condition. Now let's understand this problem in a partial shading condition with some more depth. Let's say we have a PV panel with these specifications. The output voltage is 48 volt, and the output current of the panel is 9.74 ampere, and the short circuit current of the PV panel is 10 ampere, and the open circuit voltage is 58 volt. So the electrical equivalent circuit of the PV panel looks like this. it has a current source of value ISC with a parallel in parallel with a diode. Now let's see the IB characteristics of this PV panel. Now this is the IB characteristics of the current source. If we subtract the IB characteristics of the diode from the characteristics of current source, then we get the IB characteristics of the PV panel. Now let's say two PV panels of 48 volt are connected in series, then the output voltage will be 96 volt and the current will be 10 ampere and the power output will be 960 watt. Now, let's say one of the PV panels of this series connection is shaded, partially shaded by cloud or any other object in the vicinity of the PV panel. Then what happens? The equivalent circuit looks like this. Here, the short circuit current of the shaded panel will have a lower value. Let's say it is 5 ampere. Now, since these two circuits are connected in series, the output current of the PV panel becomes 5 ampere. So here the output power will be 480 watt. Now, as we can see, as compared to the first case where none of the panels was shaded, the power output becomes half. Now, generally what is done, a bypass diode is connected across the shaded panel to bypass the current of the unshaded panel. So here the output current becomes 10 ampere, but what in turn happens here, the voltage of this shaded panel becomes zero due to this bypass diode. So the output voltage of the PV panel becomes 48 volt. So here also the power output becomes 480 watt. That is half of the case where none of the panels was shaded. So this is why series connection of PV panels in residential rooftop system is avoided. So now we know that in rooftop applications, the PV panels have low output voltage, that is in the range of 40 to 60 volt. However, we have household loads that operate at 110 volt AC or 230 volt AC. So this is where we need a power electronic interface that can convert DC to AC and also can provide high gain at the same time. So these power electronic interfaces are typically categorized as microinverters. They are generally low in power rating in the range of 500 watt to 1 kilowatt. So let's see what is the power electronics behind these microinverters. So these microinverters can actually have three different forms. The first form is the conventional one, that is the transformer based. Here we have a voltage source inverter that converts the low voltage PV source to AC, and then this low voltage AC is converted to high voltage AC by using a step up transformer. Now the problem with this transformer based form is the step up transformer used here is a low frequency transformer. So this makes the system bulky, heavy and also costly. Now, the second form here is a two-stage interface. Here, the use of low-frequency transformer is avoided by introducing a DC to DC boost stage at the input of the voltage source inverter. Now, this makes the system lighter. However, the drawback with this two-stage interface is it creates a strip DC link at the input of the voltage source inverter. Now, what this does, this actually makes the system prone to shoot through. Now, what is shoot through? If at any point of time by mistake two switches of any of the inverter legs are turned on at the same time, then it might lead to a dead short circuit across the step DC link, that is the voltage source inverter. Now this might lead to failure of the entire system. Now another problem with this two-stage interface is the DC to DC boost stage is generally a boost converter here. So this figure here shows gain characteristics of the boost converter. Now as we can see, the maximum gain that a boost converter can provide is nearly equals to 4, that too at a duty cycle, very high duty cycle, which is beyond 0.8. Now if we operate a boost converter at a very high duty cycle, then it leads to increased reverse recovery loss in the diodes of the converter. Now, the third form here is a single stage interface. It has inherent boost stage, and also it is devoid of this steep decoupling. So this single stage interface is shoot through protected. Now, if we compare these three forms, then the single stage interface is more reliable as compared to the transformer based and two stage interface. So let's look into the details of this single stage interface. Now, the single stage interface is also known as impedance source inverters or ZSI. So this ZSI has actually two stages, one the front end boost stage and the voltage source inverter stage. Now again, depending on the components in the front end boost stage, it can be categorized into passive, active, and coupled inductor based ZSI. So we'll see these three categories one by one. Now, first, under the category of passive front-end boostage-based ZSI, there are various topologies which are explored. However, these topologies have very high passive component count. So, this makes the system bulky. Also, these topologies are prone to dynamic instability. Now, under the category of active front-end based ZSI, there are various topologies like switched boost inverter, uh, QSBI, switched ZSI, and current fed switched inverter or CFSI are explored. Now, these topologies have less passive component count, which increases the power density of the system. However, the presence of the active component in the front-end boost stage increases the conduction loss of the converter. Now, under the category of coupled inductor-based FBS, there are topologies like trans ZSI, TZSI, then coupled inductor-based CFSI, and QZSI are explored. These provide actually very high gain, but these topologies make the complexity of the system very high due to the presence of the coupled inductors, and the complexity of the system increases even more due to the leakage inductance of the coupled inductors. So if we compare these three categories of the impedance source inverter, then the active front-end boost stage based ZSI seems feasible for the rooftop application uh, with higher power density and with simplicity of the system. That means less complexity. Now, under this category also, if we compare various topologies, then the current fed switch inverter, that is CFSI, is the one which has optimum component count with required high gain characteristics. So as of now, this CFSI seems the most suitable solution for rooftop application. So let's see further whether the inferences run by us so far are correct or not. So this is the schematic of the current fed switch inverter, which has active front end boost stage and the inverter stage. Now let's understand the challenges in CFSI with the help of some numeric examples. So let's say we have a CFSI which needs to convert 60 volt DC to 230 volt AC to meet the load requirement of 1 kilowatt. Now these are the governing equations in case of CFSI, where the DC link voltage VC by the input source voltage VDC is given by 1 by 1 minus 2T, where T is the duty cycle of the gate pulse that is given to the boost switch SM. And the peak value of the AC output voltage is given by MA into VDC, where MA is the modulation index of the inverter stage. So now let's say for our conversion, we have chosen T as 0.45 and MA as 0.55, then the DC link voltage VC has to be 590 volt. So as we can see here, in the active front end boost stage, almost a gain of 10 is achieved. So what this high gain does, it leads to a very high input current, almost equals to 16 ampere. So this current is high enough to cause considerable conduction loss in the converter. Now if we see, the current drawn by the inverter stage is 3 ampere, which is relatively lower than the input current. So the conduction loss incurred in the inverter stage is significantly lower as compared to the active front end boost stage. Now, this is the efficiency curve of a CFSI. As we can see, as the power rating goes up, the efficiency of the converter reduces drastically due to increased conduction loss. So, how do we deal with this problem? If somehow we can deal with this problem, then this CFSI can be used as an effective interface between the solar panels and the household load or rooftop applications. So the approach that I have used is a cognitive strategy called analogy. So the first step of this strategy is to identify an existing problem, then link it to the current problem. Then after it is linked to the current problem, we have to map the attributes of both the problems. Now the question arises, in power electronic domain, do we have a similar kind of existing problem? The answer is yes. We have these voltage regulator modules which are used to power the processors in computers or tablets. These VRMs are generally used to convert 12 volt DC to 1.2 volt DC or any other voltage level that is required by the processors. Here the current ratings are generally high in the range of 100 to 200 amperes. So here, as the power rating goes up, the efficiency reduces drastically due to this high current. Now that we have identified the problem, let's do the mapping. So on the left, we have the existing problem of this VRM, and on the right, we have the current problem of CFSI. So the mapping goes like this. So in case of VRM, we have high output current, which increases the conduction loss of the converter. And in case of CFSI, we have high input current, which again increases the conduction loss in the converter. So in case of VRM, how this problem is dealt with? So what the researchers have found out that paralleling various phases of VRMs and operating this parallel phases in interleaved fashion improves the efficiency significantly. So now the question is, can this strategy be implemented in case of CFSI also? Answer is yes, can be implemented. In fact, it can be implemented in two ways. So let's see. So in the first way, the entire DC to AC converter, that is the CFSI, can be considered as one module, and several such modules can be connected in parallel. Or only the active front-end boost stage can be considered as one module, and several such modules can be connected in parallel while keeping the voltage source inverter stage intact. Now, if we compare these two ways, then the second way seems more practical, because in the previous slides we had discussed that the conduction loss incurred in inverter stage is considerably lower than the front-end boost stage. So the second method seems practical in terms of component count also. Now let's understand the process through which I have come up with the proposed topology. So in the previous slides, we said that we are going to keep the voltage source inverter stage intact. Now to further reduce the component count, I have kept the capacitor C and the diode DA also intact. So now we are left with the inductor LM, switch SM, and the diode DM to form the module. So let's see in how many ways we can do that. So we'll see two module topology. This is a single inductor topology where the switch SM1 and the diode DM1 are connected to form one module, and two such modules are connected in parallel. Now, if we have a closer look into this topology, then in one of the operating states, the diode DM1 and DM2 get connected in parallel. So this is not a feasible operating state. So this makes the entire single inductor topology infeasible. So now let's see the topology where the inductor LM1, switch SM1, and the diode DM1 are connected to form one module, and two such modules are connected in parallel. Here, this topology facilitates the division of input current into two interleaved modules, thereby reducing the current stress in each module. So this is a feasible topology. So this is our proposed topology, which is named as interleaved CFSI or ICFSI. Now, coming to the PWM scheme of the proposed interleaved CFSI, this here shows the PWM interval in the half cycle of the modulating sinusoidal signal. It actually has two kinds of modulated intervals, power and zero intervals decided by the sine PWM and the shoot-through interval. So in converters like ICFSI, shoot-through interval is deliberately introduced to increase the gain of the front-end boost stage. So this here shows the PWM scheme of ICFSI. CFSI. Here, the Sutru intervals D1TS and D2TS are generated by comparing the triangular carrier signal with a time period of TS with two DC signals VST and minus VST, and the sine PWM is carried out by comparing the sinusoidal modulating signal with a peak of MA with the triangular carrier signal. So this sine PWM decides the gate pulses of the four inverter leg switches. Now here D1 equals to D2 is equals to D by 2. Now this PWM scheme has a constant which arises due to the fact that the Sutru interval and power interval cannot overlap, because in the Sutru interval the power active power transfer to the load is actually 0. So this leads to the constants that D plus MA must be less than equals to 1. So this here shows the PWM signals obtained from digital signal processor, where in the EPWM module the PWM scheme is implemented. Now coming to the gain characteristics of ICFSI. Now we'll compare the gain characteristics of CFSI and interleaved CFSI. So these two equations give the DC gain and AC gain of CFSI, as we had discussed earlier. Now in case of ICFSI, the DC gain becomes 1 by 1 minus 1.5D, and the AC gain becomes MA by 1 minus 1.5D. Now these equations are plotted in this figure here. We can see that the maximum duty cycle at which ICFSI can be operated is 0.67, whereas this is 0.5 in case of CFSI. So here we have obtained an extended operating region in terms of duty cycle. So this is the main reason which leads to the improved gain characteristics in case of ICFSI. That means the maximum achievable DC gain and AC gain is higher in case of ICFSI as compared to CFSI, and an increase of almost equals to 33% in AC gain is achieved in case of ICFSI. These curves are actually plotted at the boundary of the constant, that is D equals to 1 minus MA. Now let's understand this gain characteristics with some numeric example. Now suppose the DC input that we have is 48 volt, and we have chosen D at 0.46 in case of CFSI. This is actually the practical maximum D in case of CFSI. So in that case, VC, that is the DC link voltage, will be 600 volt, and the peak value of the AC output voltage will be 324 volt. Now let's take same VDC in case of ICFSI also, and take the D as 0.64, which is the practical maximum D in case of ICFSI. So here the DC link voltage that can be obtained is 1200 volt and VM is 432 volt. So clearly we can see that maximum achievable DC gain and AC gain are higher in case of ICFSI. Now this is the experimental waveform of CFSI, which captures the input DC voltage, which is 36 volt, and the DC link voltage, which is 330 volt, and the AC output voltage, that is 110 volt RMS. So here in case of CFSI, a DC gain of 9 and AC gain of 3 is achieved. Now these two here shows the experimental waveforms of ICFSI, which captures the AC output voltage and the AC output current, the DC link voltage VC, and the input voltage VDC. In the first figure, the DC gain of 14.2 and AC gain of 5 is achieved, whereas in the second figure, DC gain of 24 and AC gain of 8.1 is achieved. So this here shows the steady state waveform of ICFSI at a switching frequency of 25 kilohertz. So this waveform captures the AC output voltage V out, DC link voltage VC, and the two inductor currents ILM1 and ILM2. Now these are the switching frequency ripples of ILM1 and ILM2 in few switching cycles. Now these are the waveforms at 50 kilohertz, and these are the waveforms at 100 kilohertz. So we can see that the switching frequency ripple in the inductor currents reduces with increase in switching frequency. However, we can see that the inductor currents and the capacitor voltage, that is the DC link voltage, have a low frequency ripple in the waveforms. Now, why this low frequency ripple is there? Actually, this ripple is at twice the frequency of the AC output voltage. This is known as second harmonic ripple. Now, in case of converters like interleaved CFSI, there is a mismatch between the expression of input DC power and the instantaneous AC output power. Now, to cater to this mismatch between the input power and the output power, the passive elements in the converter, that is the inductors LM1 and LM2 and the capacitor C, act as the low frequency energy storage element. So, this leads to this second harmonic ripple in the waveforms of the inductor currents and the capacitor voltage. This plot here shows the efficiency of interleaved CFSI with respect to power rating at different duty cycles. As we can see, as the duty cycle increases, the efficiency becomes better. Now, this is a comparison of efficiency of CFSI and interleaved CFSI. So we can see that as the power rating goes up, the improvement in efficiency as a result of interleaving increases. So at 600 watt, we have almost achieved a 4% improvement in efficiency. Now this plot shows the efficiency of interleaved CFSI at different switching frequencies. As the switching frequency of the converter increases, the switching loss in the converter increases, which reduces the efficiency. Now here I'm going to conclude. So in this webinar, we saw an interleaved topology for CFSI with a Nobel PWM scheme, and also we did the performance analysis of the topology in comparison with the current fed switched inverter, and we saw a significant improvement in efficiency as a result of interleaving. Also, we achieved improved gain characteristics as a result of interleaving, and we saw 4% increase in efficiency at a 600 watt. Thank you.